What I want to discuss is optimization, and I want to introduce optimality. It will be shown in other parts. I will mention it at that moment as well. There's other topics mentioning optimization and optimality, but I want to introduce it as a piece of technology. Optimality is a tool that was developed at Cadence that is meant to do multidisciplinary optimization, so it's not specific to CFD. You can use it for power and thermal analysis, you can use it for electromagnetic analysis, and more recently we've ported it to use with the CFD portfolio, and that's what we're going to talk about today. It's working nicely with ANSA and PBS simulation from the Fidelity CFD suite, and much more that I will introduce. Optimization in automotive aerodynamics has been historically difficult to achieve through direct simulation because of the sheer cost of these simulation, right? We've seen in various presentations today that running a single simulation can be time consuming, both in terms of preparation, meshing, and CFD simulation solving has been historically the main bottleneck, right? Because running on CPUs, even on large amount of CPUs, that leads to hours, sometimes days for the higher accuracy simulations of simulation time. We've seen in recent years two key enablers that actually let this technology become much more relevant and meaningful for in-design analysis. The first of those is, of course, GPU compute, which I think almost every single talk we've heard today was talking about GPU at some point. And the second one is the use of AI. GPU gets simulation time down. That was one of the two bottlenecks, right? We get from hours to minutes for simulation times. So that means that when your simulation is minutes, basically you can start running hundreds of simulation and do a full optimization loop in a meaningful amount of time. The second one is the rise of machine learning and AI models tuned on simulation results to deliver simulations quasi-real time. That means that with GPU computing, your simulation time goes from hours to minutes. With AI, it goes from minutes to nothing, essentially. That will have huge repercussion in the coming years. Of course, pieces of technology that enable this, as I mentioned, GPU compute, and specifically the Millennium piece of hardware that we co-developed with NVIDIA, leveraging great performance and lower power consumption. That was already introduced by one of the plenary sessions earlier this morning. I will articulate my presentation around these two key objectives. First, demonstrating how Fidelity CFD and ANSA work together to deliver a great GPU workflow that basically gets you simulation time in a meaningful turnaround time. Through the use also of ANSA morphing and volume meshing and connecting all of that to optimality, we can deliver optimization workflow that leverage this GPU acceleration to achieve small turnaround time. And then in the second part of my presentation, I will show how we actually can use AI in this optimization loop to deliver essentially a full optimization on a laptop in an hour. So first, I want to take some time to show how we handle optimization using CFD in the loop powered by GPU compute. The way we did that through optimality is that actually optimality connects the whole loop, and through a morphing that is defined in ANSA with volume meshing done in ANSA Hexstream, we actually generate with optimality then the Fidelity CFD computation, the meta post-processing, and then optimality manages the optimization parameters, the definition and the steering of the morphing parameters, morphing space, and then runs all of this chain iteratively to drive an optimization workflow without the user having to do anything. What does it look like in practice? In practice, the user would set up their optimization problem by first setting up their model in ANSA, defining a few morphing parameter. I will show an example case on a driver model later that you might already have seen from some other presentations. Then you can set up your meshing and simulation setup also directly in ANSA. And once you're done, you can actually, at the click of a button, directly get everything into optimality, define some parameters such as how many samples you want to generate for the optimization, just to sort of cap the total computational time, and then run the thing and start analyzing your results. The optimization loop, of course, lets you have a look at scatter plots to examine designs, look at where the optimization is going, typical optimization analysis, such as analysis of variance, sensitivity analysis, what are the morphing parameters that are the most impactful on my design, leave one out to assess the quality of the optimization. The optimization process during the optimization actually uses machine learning to refine the surrogate model it builds to go towards the optimum design, and exploration in the form of self-organizing maps to try to identify patterns in the various parameters. The case I'm going to use for the demonstration here is the driver model. You might already have seen this particular parameterization. It was used and demonstrated at the AutoCFD workshop and published as part of the driver ML dataset. It basically uses 16 different design parameters, from vehicle length, width, height, front overhang, plan view, hood angle, but also more detailed parameters such as a few angles for the front and rear windscreen, deck lid height, taper, and some more global parameters such as the ride height, which is a global movement of the car, and vehicle pitch. Some of these parameters can also influence the length of the vehicle and the wheelbase, but it never touched the size of the wheel, actually. You can see here a few samples from that morphing space just to give an idea of the range of parameterization that we can achieve. And of course, another interesting feat from this is that since all of this is connected into a single environment, the meshing parameters actually follow the geometry automatically. So everything in terms of the size field definition, in terms of the volume refinement and surface refinement, directly follows the morphing. Meaning that if the vehicle width is increased, of course, the width of the refinement in the volume mesh automatically follows. There's no user input that's necessary for that to happen. It will follow naturally if your morphing setup is done properly. You can see a range of designs in front view and side view here. Just to demonstrate, you can see every time, maybe going back and forth between different designs with different lengths. You can see, for example, that the rear, the wake refinement there follows the length of the car to avoid any artifact coming from basically the mesh not following the geometry in the simulation space that we are defining. Just showing a side view there to give you some appreciation of what we're achieving. All of this then connects into the Fidelity CFD suite, which is also set in ANSA. Don't hesitate, we have a bunch of resources on this. Vangelis demonstrated this on the very large e-tron model, millions of surfaces earlier this morning. There's also a demo session tomorrow in session 7F. And don't hesitate also to come by. There's a booth and a demo table in the main hall about how to set up Fidelity CFD and AutoSeal in the ANSA environment and connecting that to MetaPost. So yeah, feel free to come by and talk to us. We'll be happy to discuss more. The Fidelity CFD, as I mentioned, is designed to deliver great turnaround time on GPUs. This is targeting one Millennium node. So that's a single GPU node with 8 GPUs. These are NVIDIA A100s in this particular case. So these are Millennium M1. The Millennium M2000 has Blackwell GPUs. And as you can see, the turnaround time of all of these cases is between 5 minutes and half an hour. 40 minutes for the more extreme case, more than 250 million grid elements there. There's more on the go-kart case here at the bottom, the simulation that runs in 7 minutes. There's a presentation by BMD tomorrow in session 5A, so go check it out. They're going to give more detail on how this model is set up and what sort of analysis they can perform thanks to essentially this running so fast. Of course, it's good that the solver is fast, but if it's not accurate, it's meaningless, right? We don't want a random number generator. So the solver is also validated on public and customer cases. I'm showing here some excerpts from the validation that was done for the AutoCFD workshop on the driver model with 2 variants. We validated actually the drag predictions with both RANS and unsteady scale resolving DES modeling, both of which are capable of predicting the drag and the drag direction within reasonable accuracy, which is well enough to actually drive an optimization problem because directivity and amplitude of the delta drag prediction are quite good within a few counts. We've also worked on a bunch of customer cases, some of which, of course, would highlight some limitations of the RANS and would warrant a user to go for more high fidelity methods, such as DES. This is one typical case of a hatchback model, which these types of models are known to be problematic for RANS models because of the massive wakes they can generate. So for this one, while we have decent predictions with RANS, actually we have much better predictions with DES in some of these instances. And this is the same type of validation on a compact SUV model, showing again delta drag prediction within a few counts and even closer and narrower when using a more advanced DES model. Now, what does it look like when we use this inside of an optimization loop? Connecting all of this, what we did with this driver data set is we ran an optimization using this on one GPU node, 15 DOE samples, 50 optimization samples, so that's a total of 65 CFD simulations. Each sample, due to the optimization, morphing parameter update, volume meshing, and then final solving, that leads to each sample being performed in around 2 hours. So that's about 5 days for the complete optimization. Running that on CPU would probably lead to a few weeks if you were to run this complete optimization. Either that or having to compromise on the accuracy of the solution by coarsening the mesh or not fully converging the simulation. Here, we actually ensure that the simulations are always converged and the mesh sizes are meaningful. They're actually on par with what was done for the validation study. And this workflow actually leads to a nice optimization which reduces the final drag of the base design by about 13% in about 5 days, thanks to GPU, which would be something that can be amenable in some contexts during the design cycle, but we can do better, of course, by leveraging AI and machine learning. That's what I'm going to be presenting next. AI is a change of paradigm for CFD. I think you've seen some version of this slide already. I'm going to take a bit of time to explain. So on top, what you see is your typical CFD workflow, right? You update your design, and then you churn it through geometry processing. Maybe you have to update some closing surfaces. You have to regenerate your mesh, redo the solving. All of that is quite time consuming. However much optimization and automation you can put in that process, generating the volume mesh, generating the simulation data, remains time consuming, and then you get your simulation results. When you want to do AI, actually, that becomes very different because when in use, when you have a good AI model, between design layout, so updating your design, changing the geometry that you want to look at, adding some new parts, the time between this and results is seconds. So that means, of course, that this inference is extremely fast, and that's how we can deliver optimization extremely fast. But a precursor to that is that you have to train your model. You have to actually get to a point where you have a model that gives you enough confidence that it can be used meaningfully for the type of design updates you want to do. So that's why I'm saying it's a paradigm shift. Because the time-consuming part is not generating the results anymore, is generating the model itself. It's as if you were training some CFD model to understand what design you're working on and how to solve it, right? So the training of the AI model is the part that will be time consuming. Once you have that, you can do 1 million InDesign analyses instantly. And that's what I'm going to show now. Using Optimality, actually, we can generate a DOE of hundreds of samples and simulate those completely automatically and in parallel. That's what we did. We generate 200 samples of our same data set here with the same morphing parameters and simulated all of that, right, through Fidelity CFD. Once we have those 200 samples, again, each sample will take some time to be generated, right? We can generate it in parallel, but still that part remains a bit time consuming. And then you have to train your AI model. That takes another 60 hours to actually train the model here on a single GPU. We're working on making that multi-GPU. So running that on one GPU node instead of 60 hours would be 60 divided by 8. So that becomes a few hours. And that allows us to get to a point where the confidence in the accuracy of the AI model when compared to the actual CFD data becomes about 1% relative error. So that's a few counts, which is in the same ballpark as what you can expect from the accuracy of a RANS model for a prediction of delta drag. So that should be enough to guide the directivity of an optimization process and guide InDesign analysis. Of course, we always recommend to verify in CFD at the end of the loop. Now that your model is trained, actually, you can use it to start making inference, and it will give you an idea also of its own confidence on the prediction, which is always something that you want to have because you want to know if you're starting to extrapolate from where you trained your model, right, which is not desirable. But you now get to a point where the part in between getting a new piece of geometry and the part where you get every output you need becomes quasi-instantaneous. What that means is that essentially guiding this design optimization now can be done on a local CPU laptop in this case, I think an hour and a half. The model itself, of course, for training requires larger resources, a bit more time. But once you have that model, you can actually run as many of these optimizations as you want, changing the design space, changing the parameterization, changing the constraints, changing the part you're focusing on, changing what you're optimizing. So here, for example, we're optimizing for drag, but what if you wanted to optimize for drag with some constraints on lift balance, or with some constraints on vehicle width, or with some constraint on pitching of the model, or suddenly you want to actually improve rear lift for some specific part, and then you suddenly only optimize the rear portion of your car. So all of that becomes a single 1 hour process, whereas when you want to do the complete CFD workflow, that is feasible, but then each CFD workflow will take 5-6 days. So the first time around you do your AI optimization, it will take the time to generate the model, but once you have it, it becomes extremely flexible and modular, and that becomes something realistic to use during design phase as an InDesign analysis optimization and not just producing simulation results. This is also connected with ANSA and Canvas. I strongly invite you to have a look at presentation in session 8B, which will be given on Friday morning, about the integration of these tools within the ANSA framework as well, on top of what I'm presenting on Optimality here. And that can be directly accessed for a direct inference through ANSA. So very interesting stuff. I strongly recommend you to look at this. So in conclusion, I hope I've convinced you that Optimality allows you to deliver great workflows that basically leverage what we've just said, the full suite, right? Bridging the gap between ANSA and Meta with Fidelity CFD, allowing you to reach a complete loop within the same environment. Leveraging GPU resources to make these simulations much more amenable making optimization meaningful, but also changing a little bit the paradigm of how to do design by leveraging AI, because now actually it's not a single design change that you can analyze within a day, it's a full optimization that you can carry within an hour of time. And with that, I would be happy to answer questions.
Please, any questions?
I guess everyone wants to reach the end of their day.
Sure, no, I'm sure, but, oh yeah, please.
You need to turn it on, I think. Otherwise, I can hear you perfectly fine.
So you in the optimization process, there is like 15 parameters and 50 simulations. So what's the relationship between these two numbers?
Right, so that depends on the optimizers. With the optimality optimizers, because it uses machine learning also in the optimization process, you don't need to build a massive DOE like you would in some other optimizers. Typically, our best practice is to use the same number of DOE samples as parameters. So here we had 16 parameters, we used 15 DOE. Could have used 16, just 15 is a rounder number. And 2-3 times the number of parameters for optimization, that's usually sufficient. That's also sort of what you see if you look at the optimization curve, right? It starts to plateau by the end of the optimization. Maybe running it for another 50 would yield another 1 drag count of drag reduction, but do you want to pay that expense? Maybe with the AI-led optimization, actually, you could, right? I'm realizing I forgot to mention one very important thing, that the optimal design obtained with the optimization using AI was verified in CFD and yielded the same value within 1 count. So this is a meaningful optimization that can be verified in the actual CFD.
Okay, thank you.
Sure.
How many designs you used for the training?
15. For the training of the AI model, do you mean?
Model, yeah.
200 samples.
Yes, please. Yeah.
Well, thank you, Olivier, for the presentation, first of all. I wanted to ask you, was there a difference between the optimal car by the optimizer and the optical car given by the AI training?
That's a very good question. Yes and no. The optimum design is different, mostly because the optimizer goes in a slightly different part of the space for parameters that are the least impactful in the sensitivity analysis. So there are some parameters that are less impactful, also because we tuned this based on a RANS model. Probably an LES model will show slight differences. But typically, I don't have it by heart there, but for the key parameters such as pitching, ride height, rear taper, things like that, they're exactly the same values between the AI and the CFD. Some of the less impactful parameters are slightly different, and the different optimum reached between AI and CFD changes by a few counts.
Thank you.
Olivier, just in our legacy optimization, usually we have more database or DOE than the optimization part. Now the optimization part is 50, while the DOE part is only 15. That is because we have machine learning in the optimization part?
Among other things, yes.
And can you explain other things then?
I can vaguely. So essentially, the idea is that you don't need to have a great surrogate when you start the optimization, as long as you have an idea of where to go in the space. But since during optimization we use reinforcement learning, plus it's a sort of simulated annealing, right? Where you allow yourself to jump to other part of the space to verify that you're in the right direction. What that means is that it will, one, explore the full space even during optimization, but also when it's about confident that it's reached the right place, it will start refining the surrogate model in the part of the space that contains the global optimum. That means that it's better to do more optimization samples when you do that, because you have a higher accuracy of your surrogate model. Whereas when you do a DOE, you don't know where you're going, right? You explore the full space. So you're basically shooting in the dark in the hope that you'll hit something. Whereas doing more optimization sample in that framework lets you have a much, much sharper visibility on the optimal region of the space. I hope that makes sense.
Okay, thank you very much. Oh yeah, sure. Please.
This AI will kill aerodynamic engineers.
No, it won't. No. Remember the cake. So the cake has, you need to have all the layers, right? Because to get to the point where you're happy about the AI model, you need to generate a good enough data set, right? And that data set can only be obtained with high accuracy CFD, right? So you still need to have a high-end CFD solver that will deliver you both high accuracy and short turnaround time, because you want to generate many samples. Now, of course, once you already have that database, you can keep enriching it and enriching your AI model. But if I have an AI model that is trained to do a car and you ask it to do a motorcycle, it won't be happy about that. So you still need to be able to inform the AI model, right? This is data-driven. But the data has to come from somewhere. So pure simulation, that's physics-based, right? And AI is data-driven, so to feed the data, you need a physics-based simulator. So that will not go away. It will just, it's a change of paradigm.
Okay, thank you very much. Thank you again, Olivier.